This brings us now to the forward kinematics that we can try to extract and write down out of the DH parameters. So for the forward kinematics, we define the transformation matrix from one frame to the other frame in terms of joint variables. Okay, so that would define my forward kinematics. So if you look at this, again, this is a general link I-1, that's attached to axis I-1, that joint I-1, and then on the other side I have axis I for joint I. And as you can see here, this link is twisted and it has a twist angle. You can see this Zi-1 and Zi, okay? And there's a common perpendicular between Zi-1 and Zi, which is this line right here. All right, and this is the other common perpendicular between Zi and Zi plus 1. It's not shown, but this is the common perpendicular between them. And you can see here the four parameters, the DH parameters. This is the alpha I minus 1, and this is the AI minus 1, and the DI and the theta I. Okay? Now, in order for me, as we saw and covered in chapter 2, in order for me to go from one frame to another, I can have a transformation matrix that describe one of the frames relative to the other. So in this here, I'm going to try to go from the origin of frame I to the origin of frame I, the origin of frame I minus 1 to the origin of frame I, right here. Okay, so to go from here to here, the first thing I need to rotate about x-axis by the amount of alpha I minus 1. Okay, this is my x-axis, xi minus 1, and I'm rotating by the amount of alpha I minus 1, which is this right here. All right, so that takes me for the first transformation matrix that includes R, rotation about alpha I minus 1, and the translation section in this, which is the fourth column, would be 0, 0, and 0. Okay, so now I rotated in place right here. The next thing is I need to move my frame from this point after rotation. I need to move along the x direction, the new x direction, and come to the intersection with the next z-axis. Okay, so I need to move along this common perpendicular by the amount of a I minus 1. So that would make me multiply this rotation matrix by not rotation, this is transformation matrix that has rotation and 0 translation. And then I have to multiply it by another transformation matrix that has identity rotation and it has translation along the x direction by the amount of ai minus 1. Okay, so that takes me from this point to this point. Now the next motion I can do is I need to do the rotation to take my x-axis from here to here. Okay, so I need to rotate about z-axis, zi, by theta I. Okay, so I can multiply this by another transformation matrix that includes rotation about z by the amount of theta I, and the translation portion for this one will be 0, 0, and 0. Okay, so now my frame becomes my x. All right, and then the last motion I have to move is I have to move from this center to the next center, okay, which is the center of frame I, and this motion has to go along zi by the amount of di right here. So again, I multiply this by another transformation matrix that has identity rotation, and then the translation part has di in the z direction. Okay, so if I multiply these four transformation matrices, then I'll be describing frame I relative to frame I minus 1. Or I can think about it in a different way. I'm moving from frame I minus 1 all the way to frame I. Okay? Now I know how to create a transformation matrix for this part, and another transformation matrix for this part, another one for this part, another one for this part. If I create all four of them and multiply them together, I will come up with this total transformation matrix that would describe frame I relative to frame I minus 1. Okay? So now if I have all the DH parameters that show the relationships between frames I and I minus 1, then I can substitute them here, or I can use these individually, as we will see in an example later on. Okay? Now, once I find the transformation matrix from one frame to another, I will repeat this for the other frame and then the other frame all the way until I reach my end-effector. Okay? And then once I reach my end-effector, I can find the description of frame N, which is the gripper, in reference to frame 0, which is the ground, by multiplying each one of these transformation matrices that describe one frame relative to the previous frame, multiply them together in this fashion. Okay? So T01 times T12 times T23 all the way up to Tn minus 1n. Okay? So that would describe the transformation matrix for frame n in reference to frame 0, or I can think about it as transformation matrix that takes me from frame 0 into frame n. Let's take an example now on how to do the forward kinematics and find the transformation matrices. For the shown RPR robotic manipulator, the DH parameters table is defined as shown. Calculate the transformation matrices T01, T12, T23, T34, and then find T04, which is the total transformation. This is my robot. We solved this in an earlier slide. We assigned the link frames and we found the DH parameters, which are shown right here. Okay, so each one of these lines include the DH parameters that describe the link from one frame to another. So if we use these parameters for the transformation matrix that we defined earlier, then we can find the transformation from one frame to another. So from frame 0 to frame 1, we use this. Frame 1 to frame 2, we use this. And then from frame 2 to frame 3, we use this. And frame 3 to frame 4, we use this line. Okay? So we're going to use these lines and substitute with the transformation matrix so that we can find each individual transformation. And then we'll multiply these transformations to find T04. Now to start the solution for this problem, I put here the reference for the general equation for transformation. So I put it here in terms of the 4 different transformations that would take me from frame I to frame I minus 1. Or from I minus 1 to frame I, and then I also put the resultant transformation matrix after multiplying all these 4 together. Okay, and this is the DH parameters for the problem that I have at hand. So what I'll do is I'll find T01, and then for alpha 0, A0, D1, and theta 1, I'll substitute them here. Or I can look at this. Since the first alpha here is 0, that means rotation about x by alpha would be identity, right? So this would be a 4x4 transformation matrix that would be identity matrix, all right? And then because the a here is 0, that means dx or translation in the direction of x by the amount of ai minus 1 would be 0. This a is 0. So this would be a 4x4 transformation matrix that would be identity matrix. Now here, this is rotation about z by amount of theta I. So this is a variable. So this will be a 4x4 matrix. Okay. And this d here is another transformation that would have identity rotation, but then it will have a translation in the z direction by the amount of di, which in this case will be L1. Okay. So in this case, I can ignore the first 2 matrices right here because they are identity. And then I can just multiply this matrix by this matrix to find the final transformation matrix T01. Okay. Or if it's easier, I can just go ahead and substitute directly here. I already know that alpha 0 is 0, so I can find everywhere that I have alpha, I can substitute by 0. And the a here is 0, so every time I have an a, I substitute by 0. And d1 here is L1, so every time I have d1, I substitute by 0. And then theta 1 would be variable, so I can leave it here as a variable. So let's start with T01. I'm going to be using the first line for T01. So I'll have rotation about Z by theta 1. Again, this is identity and identity. So here I have rotation about Z by theta 1 right here, multiplied by translation in the Z direction by the amount of L1, which is D1 right here. Okay, so if I have a 4x4 matrix for this and 4x4 matrix for this, I can multiply them together and come to this 4x4, or I can substitute directly here to come up with this 4x4 transformation matrix. Okay, so that's T01. For T12, as you can see here, I have a value here. So this rotation would have a value. It will not be identity. So I have rotation about X by 90 degrees. I'll put it in the form of transformation, 4x4. And then I have 0 here. So that D would be identity matrix. So it does not have to be there. And then I have R about theta. And this R here is 0. So again, this would be identity matrix. So I don't have to include it here. And then the last thing here, I have translation in the Z direction by DI, which in this case is D2. And this is the variable for my prismatic joint. So I will leave it as a variable. Okay. So at the end here, I'll have a 4x4 transformation matrix that includes rotation about X by 90 degrees. And then a 4x4 transformation matrix that includes identity rotation and a translation in the Z direction by D2. Okay, so I can either multiply these two transformation matrices together to come up with this, or I can just substitute the values from this line directly into this equation here. Okay, now similarly we can find T23. We use the third line here, and we have the first two values as zeros, so that would eliminate the need for the first two transformation matrices, and we only need these two that we substitute theta I by theta 3 and di by L2. So if we do that, we can either multiply these two matrices together to find this, or we can substitute the values from this third line using this equation to come up with this. Now for T34 transformation from frame 3 to frame 4, if you look here, I have the first two values here for this fourth line, zeros, and the fourth value is 0, and the only thing I have is L3 for the D. So that means this will be identity, this will be identity, and this will be identity. This will be identity. This here I'll have a 4x4 with identity rotation matrix and a translation along the Z direction by L3, which is di here. Okay, so again, in this case, I have only one transformation matrix, so I don't need to multiply anything. I can just fill it out. The first portion would be identity rotation, and then I'll have translation in the Z direction by L3, which means it will be 0, 0, L3 here. Okay, so again, I can just look at this, or I can substitute this fourth line into this equation to come up with this one. So, the way I like to do this, when I have something simple like this, I just go directly with this equation, because all of these identities, so I can ignore them and take this. I don't have to multiply anything. But when I have a lot of numbers in that line, then it will be too much to multiply too many matrices here. In that case, I'll go straight with this resultant transformation matrix. Okay, so now I have the description of frame 1 relative to frame 0 here, and another description of frame 2 relative to frame 1 here, another description of frame 3 relative to frame 2 here, and another description of frame 4 relative to frame 3 here. Now if I need to find the description of frame 4 relative to frame 0, all I have to do is multiply all of these matrices together. If I do that, and multiply all these transformation matrices together, I find T4 relative to frame 0. Okay, after the multiplication, this would be my 4x4 transformation. Now I want you to notice that each one of these transformations has only one variable, and in this case it's theta 1. Okay, when I say C1 here, that means cosine theta 1. minus S1 is cosine minus sine theta 1. Okay, so here, this one here represents the first pair of joint and link. Okay, and for that pair I have one joint, that means I have only one variable. And here I have a second joint, which is a prismatic joint. So for the second pair of joint and link, I have one variable here, which is D, in this case D2. And then for the third transformation, this is from the third pair of link and joint. And again, I have one variable, which is theta 3. In this case, this is a revolute joint. And then for the fourth transformation, remember, the fourth transformation, I have no joints at all. This describes the end effector relative to frame 3. So there are no joints between the end effector and frame 3. Okay, so that's why this whole thing is constant and I have no variables in here. Now when I multiply all three of these together, my transformation matrix will have three variables, which are the three variables for the joints, theta 1, d2, and theta 3. Okay, you can see here, this is C1, that means cosine theta 1, C3 means cosine theta 3, and here I have d2, which means that this is the variable for the prismatic joint. Okay, so this would carry the 3 degrees of freedom variables, or 3 joint variables, that would be used for forward kinematics. So if I would like to find out where the end effector be in space when I'm given specific joint values, I can just substitute these joint values here. I need 3 joint values because I have 3 joints in my robot. So if I'm given theta 1 and d2 and theta 3, I can substitute them here, and then I can find out where is the end effector frame relative to the ground frame. Okay, so this is what we call forward kinematics. Here are a couple of notes about joint space and Cartesian space. I would like to talk to you about the difference between joint space and Cartesian space and what we mean by each one of them. Joint space is the space that contains joint variables. So if we have a robot that has 3 joints, for example, that means we have 3 variables. So that would be the joint space. If we have a robot that has 15 joints, that means the joint space will have 15 variables. Each variable carries the variable for that joint. Okay, so the joint space describes how many joints you have in your robot. All right. Whereas Cartesian space is the space that contains the Cartesian variables at the end effector. So if you think about the end effector, where can the end effector go? It can go in the x direction, y direction, z direction, and it can rotate about x and y and z. So that would make a total of 6 degrees of freedom at the Cartesian space. Okay, in the Cartesian space we can never go more than 6 degrees of freedom because in 3D space we have x, y, z variables and rotation about x, y, z variables. Now if we talk about a planar robot cannot go in the z direction, so that would have only 3 variables, which include translation in x, translation in y, and it can also rotate about z, which is the same plane where x and y is. Okay, so that only gives it 3 Cartesian degrees of freedom. All right, but if we have a full 3D robot that has lots of joints to move anywhere, the Cartesian end effector will move anywhere in the Cartesian space. That means we have motion in x and y and z, and we have rotation about x, y, and z. Okay, which is of course the maximum number of Cartesian space variables that we can have. So whenever we talk about joint space, we're talking about the number of joints in your robot. And whenever we talk about the Cartesian space, we're talking about what directions can the end effector go when we use this robot. And the end effector can go in any one of these 6 directions, or maybe part of these 6 directions. All right, so we always have to think about this when we control the robots, when we control them using the joints, joint control. That means we are controlling the joints to go to whatever place it goes to in the Cartesian space for the end effector. But when we control the robot using the Cartesian variables. That means we are controlling where the end effector goes precisely, and then we have to find out what are the joints that are needed that correspond to where the end effector is. And we're going to see this in the inverse kinematics chapter, which is chapter 4. Here's an example of an industrial robot that's called PUMA 560. And this is an industrial robot that's been around for decades. And it has 6 revolute joints, so 6 axes. And it's designed such that the end effector can travel in all 6 Cartesian space directions. So it can travel, the end effector or the gripper can travel in X and Y and Z. And it can rotate about X and Y and Z. So the following figure here, or the figures will show pictures of the robot that you can see here. Okay, so that's the PUMA 560 robot. This is the first joint, upwards, up and down. This is the axis for it. And then the second joint is right here. This is the axis for it. And then the third joint is this elbow. And then there are 3 joints here. One of them with the axis this way. And then another one with the axis at this point right here, which is this way. And then a third axis, which is this way, that you see at the flange at the end there. All of the axes are revolute joints. And then we can see this drawing here that shows all 6 joints and the axes for these joints and the limits for all these joints. Okay, so this is a very famous robot that has been used a while. And we have it also in the lab. You are welcome to come and take a look at it. Now, if we want to assign the frames, I'm showing here the figures that shows the frame assignments for the PUMA 560 robot. And you can see here that for frame 1, we have the Z1 here, which is the rotation axis. And then we have X1 and Y1. And then at that same point, this arrow here is pointing that this frame 2 is at the same point where frame 1 is. Just so that it can be clear, it was taken out, but this belongs right here. Okay, so we have Z2 as this, which is similar to Y1, and then Y2 is going downwards, an extension of Z1, and then X2 is going this direction, which is the same as X1. Okay, and then this is frame 3 right here, and frame 3 you can see Z3, which is the axis of rotation here, and then you have X3 and Y3 in these directions. Okay, and then frame 4 is not clear here, so I have another picture for frame 4. So you can see here frame, actually this one includes actually from frame 3. So frame 3 can be seen here in 2D, which is the same as the one you see here. And then frame 4 here we have the Z downwards in that direction. This is where the joint is, so that rotates about this axis. And then this is X4, and then you have frame frame 5 at the same point. All frames 4 and 5 and 6 are the origins for them are the same point right here. Okay, so joint 5 is this joint right here, and it rotates about the axis that is going into the board or the screen. And then this is the X5 and Y5. The origin is also right here. Now for the 6 axis, this is the flange that rotates, and it rotates about this axis. Okay, so this again, the origin of frame 6 is the same point here where frame 5 and 4 are, and we have Z6 downwards and X6 towards the right in this configuration. Okay, so these frame assignments are in the textbook that you have for this course, and you can go and see how it's assigned in there. Now, after assigning the frames, we can extract the DH parameters, and they're extracted right here. Remember, we have 6 frames, 6 joints, and 6 links. So each one of these lines indicate a pair of link joint. So this is link 1, joint 1, link 2, joint 2, all the way down to link 6 and joint 6. Okay. It does not describe this up to the end effector. It only stops at the flange. All right. So this is the DH parameters for the PUMA 560, and then we can use each one of these lines to find the transformation matrices. So this is T01 using the first line, obviously, as you can see here, there's only one variable, theta 1. So you have only rotation about z-axis by the amount of theta 1 and no translation. And then for the second line, I got t12. So this here is t12. And then for the third line, I got transformation 2-3, as you see here. The fourth line, I got transformation 3-4. So in a case like this, as you can see, all parameters, all four of them have values. So for this case, I would rather use the general form of the transformation matrix rather than having 4 transformations for each one of these values and then multiply them together. Okay, and the case, for example, in this case, the first line, the first 3 transformations are identity matrices. So all I have to do is just put the transformation for the rotation about z in here, which is what we have here. Okay, and then for the fifth line, I found t4-5, and on the sixth line here, I found t5-6. Okay, so these are the 6 transformation matrices that describe each individual frame in reference to the previous frame. Now, if I multiply all these transformation matrices together, of course, they have to be in order. So T01 and then 1, 2 and then 2, 3 and so forth. I can come up with a total transformation matrix that describes the flange or the end-effector place where you place it in reference to frame 0, which is the ground frame for the PUMA robot. Okay, so I multiply these together and you find this. Of course, this is a huge matrix, but it's in the textbook. So I encourage you to go back to your textbook to look at the details and read the details on how the frames are assigned and how the DH parameters were found using the dimensions. And then you can also look at the total transformation matrix that was also described in your textbook.